So now that we are clear about the main idea of how to do hypothesis testing for a mean of a population, we can apply the same logic to a more realistic situation of not knowing the population standard deviation in advance. Because that's what you expect. You are trying to test something about the population using a sample. Most likely you wouldn't know what is the standard deviation of the population. You're still assuming that the population is normally distributed, but you don't know what the standard deviation is. So as you should be expecting by now, having done it many times, that exactly the same logic as from last two lectures can be used, except for the fact that for the sample mean, we are going to use t-distribution instead of the standard normal distribution. And we'll pick up the sample standard deviation. We will use this sample standard deviation instead of the population standard deviation. So we don't know the population standard deviation and want to do hypothesis testing for population mean. So since you don't know this standard deviation, so the solution is that use sample standard deviation to estimate population standard deviation. Estimate, or the correct word should be replace. And when we do this, the only difference which occurs is that the z standard normal distribution is replaced by the t distribution. So now our main assumption becomes that the sample mean is following the t distribution. So before, if we wanted to test, so let's say this is what you want to do. You want to test this null hypothesis. Let's say the null hypothesis is that the population mean is less than or equal to a certain value, and you are testing it against the alternate that the mean is greater than this value. Instead of this, your h naught could be that mu is equal to mu naught, and as long as you take the alternate that the mean is greater than this value, then the logic would be same, because this is just, when you use this, you are just picking the extreme value from these possible values of the means, and this whole range is your h naught, and this is h1. So the logic is same. Previously, we used this criteria for rejection. Reject h naught if your sample mean, the sample mean which you got in your sample, is greater than a critical value, which you compute by doing this. This will be changed to reject your default hypothesis if your sample mean is greater than this critical value, which now is given by mu naught plus, instead of standard normal, you have the t-distribution. And t-distribution has an index depending on how big is your sample. And again, this alpha is representing significance of the test. This is sample size. And again, so you just replace the standard normal with the t, and this population standard deviation is replaced by the sample standard deviation. While this was the population standard deviation, which you are assuming that you don't know. So you use the sample. So it's just exactly same, just replacing z standard normal with the t and population standard deviation with the sample standard deviation. Similarly, if we have to test on the other side, so over here, your hypothesis was that mu is equal or less than mu naught. If you have the population mean, this is your hypothesis, or this one. But the alternate is this. In this case, this is the only alternate possible. In this case, you could have a two-sided alternative, but if you stick to one-sided alternative, because you are suspecting that it can go in that direction, then we will use this test. So just like before, let me just write what we had before. Or let me just write the final answer. Reject H naught if X this time, if your sample mean this time is less than the critical value. Instead of being more than critical value, since you are looking on the other side, you're testing here a critical value. Some small number here will be your critical value. If you are less than this, where this is given by your assumed mean minus this number. So I was able to write it because the t-distribution is also symmetric. So this, in principle, I should be writing this critical value, T bar T n minus 1 alpha, where this is defined by probability of T being less than T bar n minus 1 alpha is equal to alpha. But this would be same as probability of T greater than Tn minus 1 alpha, some value here. So this area, they're both same. And because of the symmetry, these two numbers are related. It's just minus Tn minus 1 alpha. So over here, I could have written it like this. But because of the symmetry, I can just compute this kind of critical value and put it here. So I should have mentioned here that what is this critical value? I didn't mention it because it's exactly the same logic as in case of the standard normal. Since you're looking on this side, if you get a number far away on the right hand side, in this case, then you reject. So T is greater than this critical value. The probability, if the probability of the T variable being greater than this critical value is equal to alpha, then this is the critical value you have to pick. So exactly same what we did in last two lectures, just replacing Z by T and sigma, the population standard deviation, with the sample standard deviation. Now, we can also consider the two-sided distribution. So while for the two-sided alternatives, so if you have H naught, that mu is a particular value, and you fail the test if you are getting a number bigger than this or smaller than this. So you have a two-sided alternative, which you just write mu is not equal to mu naught. So you will reject if your sample mean is less than. So you have now on the two side. If you get a number way over here or way down here, in both cases, you reject. And your significance is, if it's alpha, you divide half of it here and half of it here. So reject if your sample mean, what you got in sample, is less than this critical value, lower critical value. You just change alpha to alpha by 2 because you only want to give half of the significance here. Or if your sample average is greater than the upper critical value, So there's literally no other difference except for replacing the standard normal with the t and replacing population standard deviation with uh, sample standard deviation. Perhaps we can do an example. So you are given so suppose someone claims that the average population average is 20. So maybe let's say there is some uh, boxes which are being filled, and it is claimed that the average weight is 20. Now you want to see if this is true. So this is your H naught and you want to test it because it is not desired that there's more stuff in the box or less. You don't want to waste and you don't want to under fill the boxes. So you are taking the alternate that mu is not 20. There's some other average value for the weights in the boxes. So it's a two-sided alternative. And you don't know anything about, don't know anything about population standard deviation. So what you do, you want to test it, want to test H naught. So what you're gonna do? Well, you can pick a sample. So pick a sample. Suppose a sample of size n is equal to 9 was picked. So 12 boxes were picked. And these are the numbers you got. Now, in order to test, in order to proceed, you need to compute the critical values. But to compute the critical values, you need the sample standard deviation. Also, once you have the critical value to test, you need sample mean. You will compare it with the critical values. And what you're going to compare? Your sample means. So we need these two numbers computed from this data. So let's do it in SPSS because it's a bit quicker. So I have the data here, and I have already filled in this data. And what I'm going to do, go to descriptives. I have this variable written over here. Choose options. I need mean. I need to compute mean and standard deviation. So when I do that, I find that the mean is, let me show you in the screen. I found, this is what I found, that the mean is 20.3556 and standard deviation is 0.6126. So let's note it down. So the mean is 20.3556 and standard deviation is 0.6126. Now there has to be specified a significance level. So suppose test with a significance .05. So now since I have a two-sided hypothesis, alternate hypothesis, so I will have to divide the significance on the two sides. So alpha by 2 would be 0.025. And now I can compute this critical value. I have 9 data points, so n minus 1 is 8. This I need to compute. So what is this? This area being 0.025, this number I'm looking for. This critical value, so that this area is 0.025. And by the way, this would be same as this area, which would be minus t 0.025. I'm dropping the index 8. I just didn't want to write it. Maybe I should just write it. So how to compute it? You can go look in the table. Let me do it from SPSS. So I go to transform, compute variable. And since I'm computing a critical value, I have to go to inverse distribution functions. I go to inverse t, and I have to specify a probability. Since it computes the cumulative probability, so in order to get this thing that t is greater than that t critical, I'll actually be computing t less than being that critical value. So the total cumulative probability would be 1 minus alpha by 2. So 1 minus alpha by 2 would be 0.975. And wait, let me see if it's visible. I hope it's showing up there. 0.975, and I put in the degrees of freedom. Which are 8. Let me write a target variable, critical. So I get the answer 2.31. So this is 2.31. So now I can compute the upper critical value. That's going to be 20. My tested mean, the mean which I'm testing, plus 2.31 into 0.6126 over 3. So this is 20.47. And this I am testing again my sample mean, which is 20.3556. And since the sample mean is bigger than the tested mean of 20, I don't really need to compute the lower critical value. The role of having a lower critical value was only that significance was divided into 2. So I can test, and since x bar is less than no upper critical value and still larger than mu naught, so that means it's larger than the lower critical value, which is always less than the tested mean. So I cannot reject, because I could reject if x bar were greater than the upper critical value. It's not. Or if it were less than the lower critical value, but it's bigger than the lower critical value and it's less than the upper critical value, so I cannot reject h naught at significance 0.025. However, I can still say that I have evidence in favor because I'm seeing a number. My sample mean, let me see if I have the correct, yeah. My sample mean is, where is it? Yeah, 20.3556 is larger than the claimed value of the mean, which was 20. So I have some evidence. There is some evidence that the mean is probably, when I say mean, I mean the population mean. The sample gives you an evidence for the population. Mean may be bigger than But the evidence is there, but it's not strong enough to claim it at a significance of 0.05. So how strong is that evidence? We can find out by computing the p-value. But how strong is this evidence? For that, we need to compute the p-value of this sample. So how am I going to compute the p-value? So basically you are saying if we can reject H naught with what minimum significance can it be done? So that's that minimum significance you are trying to find out. And how you're going to do it? By putting the upper critical value equal to what you actually got, because that's the maximum you can do. So this is what you got, and this is equal to the population, and the one which is claimed, plus, now this time you do not know the critical value. This time you will compute the critical value from this formula. This is 0.6126. What is this? This is the sample standard deviation, and divided by 3, which is under root n. So you just bring it here and multiply. So this gives you is 0.3556 times 3 over 0.6126. And if I do the numbers, I get 1.7414. And you have to find out, now this time you have the critical value. This is the T graph. And you know, T graph is also centered around 0, always. You know that this number is 1.7414. You want to know how much is the area? Compute that area, the T is greater than this critical value. Which you know what the value is, 1.7414. You want to know what is this? And that will be your alpha by 2. So if you do that, look it up in the table or in the SPSS. Let's look it up in the SPSS. So transform, compute variable. This time you're not looking for inverse one. You are instead looking for the cumulative distribution, and cumulative distribution for t. Now your quantity, the value is 1.7414, and numbers of degrees of freedom was 8. So when you compute, you get 0.94. But this is the cumulative distribution. So what you have computed is p t greater than this value of is 0.94. But so you have computed this area because that's what the cumulative distribution gives. But you want this area. So this is just going to be 1 minus 0.94. So that means alpha by 2 is 0.06. So that means alpha is 0.12. And this significance is your p-value. Is 0.12. So we can still reject H naught, but with a p-value of 0.12. So you couldn't reject it with a significance 0.05, but you can report that it is rejected with a p-value of 0.12. And the person who is reading it, they can draw whatever conclusion they can draw from here. So they will conclude, well, there is evidence in favor of rejecting this claim that the mean is 20, but the evidence is not very strong. Why? Because p-value is not small enough. So evidence for rejecting H naught is not strong. Now, this kind of same logic can be applied to test population proportions. Using our knowledge of sample proportion distribution. Because we had the result that if the population proportion, because we know if the population proportion is P, let's say, then the proportion in the sample which I'm writing as a small p, I'm putting a head on it, is a random variable with normal distribution having a mean, so it's still centered around the population's original distribution, and standard deviation given by this number, where n is sample size. So the variable, this is all what we have done long time ago and many times over. So this is all I repeat all these things many times. So it's just a revision. So this variable, because of these properties, you know that if you are given, if you're told that a certain variable is normally distributed, like we know that this p hat is normally distributed, and you know its mean, and you know its standard deviation, you can compute, you can calculate, you can define a variable which will have a standard normal distribution. So this variable has a standard normal distribution. So using this fact that this variable has a standard normal distribution, you can devise tests to test a claim about the population's proportion. So, for example, if you have, wait, so you want to, for example, if you want to test the following hypothesis, that the null is that the sample proportion is equal to P naught, or let's say not sample, the population proportion is a certain value, or for this case, that the proportion is less than a certain value, and your alternate is that the proportion is actually larger than this claimed value of P naught. So how are you gonna test it? Well, if you think about it, what we just said, that this guy is a standard normal. So if I think of in terms of the original variable P hat, so P hat would be distributed like this, centered around P naught and going larger than that and smaller than that. So if P hat, so my alternate is that the the population proportion is bigger than this value. So if in my sample I see numbers here, it could be because of two reasons. One reason is that it's just by chance because my P hat is a random variable and it will take values all over here. It can take any value here with a certain probability. Or it could be because that the P naught is not actually situated here. P naught is bigger, is somewhere here. So in other words, I will be failing the test if I see a value of P hat much bigger than this claim value P naught. So will tend to fail if P hat is much bigger than P naught. But if P hat is much bigger than P naught, that means this variable. So on top of it, I can draw the Z graph, Z centered at 0. So Z would be landing here. Because if I got a p hat, a sample proportion equal to p naught, I'll land at 0. And that would be most probable thing. But if you're landing way, way far over here, so when p hat is much bigger than p naught, z hat would be much bigger. By much, you have to define how much bigger than 0, because it's going on the right hand side. So there's a critical value is a critical value of z, say z hat alpha, because this critical value depends on with what significance you are trying to reject it. And so that if you see a z hat greater than this critical value, you will reject. And how is this critical value computed? Again, if z is larger than this z alpha, chances of that happening should only be alpha. That's the definition of, just like before, of z alpha. So that means if I write this equation, this is saying p hat minus p naught over 1 minus p naught, because in the original formula you have the population proportion coming in here. So we just use the assume one because that's what we're testing. So I write this equation, I just open this up and it's saying that this should be greater than z alpha. And that means p hat is greater than the small p hat sample proportion is greater than this population from population proportion by this much. I just took it on this side and bring it here. So if this happens, then you reject with a significance alpha. On the other hand, if I have the opposite, on the other hand, if you had that H naught if H naught is that P population proportion is bigger than a value, and you alternate is on the other side, that the population proportion is actually less than this claimed value P naught. So again, if I think in terms of the standard normal, P hat would be centered around this value P naught, and I will be tending to reject if I see much smaller value of P hat. So if p hat is smaller, z hat will be much smaller than 0. See, if you look here, if p hat is smaller than p naught, then z hat would be negative, because z hat is centered around 0, and you will see a value here, which I can call z bar alpha, where this area is alpha. But I know this would be same because of the symmetry as z alpha, where this area is alpha. So I can just use that notation, and this is equal to minus z alpha. This number, wherever it lies on the other side at the same distance from the central value. So you can say that reject H naught if you see a value z alpha bar which is even less than this critical value. Or this you can write as minus z alpha is less than this value. So if I just take that to the other side, this is all this is saying is if I see in my sample the proportion which is less than the claimed value by this amount. So again, it's the same amount. In that case, it was added. In this case, it's subtracted. Similarly, you can do a two-sided test. You will be computing the lower critical value like that and upper critical value with a plus sign. And if you see in your sample a proportion which is larger than the upper critical value or less than the lower critical value, you reject. As simple as that. Now, probably we can do an example. So suppose some company, tutoring company, claims that whoever takes their course, they pass an admission test of a university. That 70% of the people, at least 70% of the people pass the test, admission test of a university who take their course. So what they're claiming, among all the population of the kids who take their course, the people who pass, their proportion is bigger than 0.7. So that's their claim. And you want to test it. So your alternative is that it's actually not 70% who pass, so it's less than 0.7. And you want to test it with a certain significance, let's say significance alpha is 0.5. Now you want to compute the critical value. So since you are looking for your alternate is that it's less than this, so your population critical value would be P naught minus Z 0.5 times the claimed values. And suppose you did it on a, you want to do this test by looking at the results of 100 students who took the course and then they failed or passed in the admission test. So that's what you have. So critical, this would be 0.7 minus Z, sorry, this is not 0.5, I should be saying 0.05. And we can compute what is Z 0.05, and that is wait. So we know that if I compute this, it's 1.645. So I get 1.645, and this number gives me 0.7 into 0.3 square root divided by 10 gives me 0.04558. Well, I missed a 0. Times 1.645. So this is 0.7 minus this number comes out to be 0.075. So 0.7 minus 0.075 gives me 0.625. So I will be able to reject it based on a sample of 100 people if in my sample proportion less than 62.5% are passing the test. So suppose I pick this sample of 100 students, and in my sample only 60%. Well, there were 100 students, let's say only 61 passed. Based on this, I'll be able to say reject their claim at 0.5 significance level. They can still be true. They may still be true. It may be your bad luck that in this sample you picked up on 39 of them failed for some reason. It was just by random chance you happen to pick up those people who failed. But based on this sample, you're gonna say that I reject their claim, although they could still be true, which is written over here, that there is a slight chance, there's a 5% chance that their claim could still be true. So I will probably, so similarly, you can, using the same logic in this case as well, case as well, you can compute the p-values. So suppose you found that only 59 passed out of 100 in your sample. So you will put this sample proportion equal to the critical value. And that would be P naught minus Z alpha over here is the claimed value. I have to write it as a proportion. And you put in the numbers here. Compute this. This will give you a number. And then you find the probability for Z being greater than this number. That would be equal to your p-value. Maybe I can just do it. So this number, when I bring it here, I get, well, I can bring this here and bring it here. I get Z alpha is equal to 0.11. And this number then gives me 0.7 into 0.3 square root. Sorry, 0.7 into 0.3 square root divided by 10 inverse times 0.11. So this gives me 2.4. So for this Z over here, 2.4, I want to compute this. And when I do that, I get 0.008. This number is 0.008. So that means p-value is 0.008 because you had less number of students passing compared to your critical value. So you could increase the significance of your test, and that, I mean, increase in the sense that it's a stronger evidence, and the p-value turns out to be 0.008. So that I'm gonna stop here.